Well, hello. Maybe you got here by way of my other video. I made one on just the idea of impulse and momentum and the connection between the two and how we can use that idea to solve a physics problem. And in that, I mentioned that there's a few different forms that impulse might take in a typical problem, one of which is the area under a force-time graph. And so I wanted to expand on that a little bit here and show you an example of one of those. So there are times where forces are kind of hard to describe. Very common in nature for forces to not be nice, steady, constant forces, but maybe be changing over time. And so one great way to represent something that changes over time is by way of a graph. So I'm going to make a graph here that shows a force that lasts for maybe 5 seconds. And I'm freehanding this. Typically you would use grid paper or something like that, but I'm going to draw it well enough that I think we can use it. So now forces are vectors. They can be rightward or leftward. They could be up or down. So we've got to account for their direction, and I'm going to allow for some negative forces here. So maybe all these are my positive forces. That might be pictured as being pushed rightward. And down here I might have some negative forces or things being pushed leftward. So I'll give my graph a label on the vertical axis. That'll be force in newtons. And if I want it to last for 5 seconds, this is a little hard to do without grid lines, but I'll just put 5 tick marks there. 1, 2, 3, 4, 5. And this will be my time in seconds. So there's a typical force-time graph. And I will tell you this, whenever you see a force-time graph, 99% of the time, you're going to be asked something about impulse or change in momentum. Now, it might take a different form, but I'm almost certain that's what you're going to end up using. So let's make up a graph here that might be useful. So perhaps for the first 2 seconds, we increase from 0 newtons up to 4 newtons. So maybe something like that. Again, freehanding here, so pardon me if it's a little rough. And maybe over the next 2 seconds, we go back down to 0. And actually, maybe that force change continues. So by the time we're at 5 seconds, we've made it down to -2. So we can at least use my horizontal lines here to reference where we ended up. I'll put a little dash line here just so you can see we ended at 5 seconds. So let's calculate the impulse that we would find from this. And you may have done this in other classes where you needed to find an area. The area, we call it under the curve. But in this case, we don't really have curves. We have lines. And mathematicians will call lines just straight curves. It sounds a little bit like an oxymoron, but it actually is okay. And we sometimes say under, even when we mean over. More technically, we're always referring to the area between the horizontal axis and the graph itself. So I always recommend that you shade that region yourself. Now, if you're using it from a textbook, obviously don't draw in your textbook. If you're a high school student, you're not supposed to do that. But if you want to just draw it on your paper, then that gives you a place to shade, because I want to show you what this area looks like. Now, I'll suppose we want the impulse over the entire 5 seconds. So here's where people will make a mistake. They'll want to go all down here underneath the time axis. But the area has got to stop right here at the time axis. So just that shaded region there. Plus, here's the time axis and the graph and the space in between that. So what do we do here? Well, we treat all of this above the time axis as positive impulse because it's due to these positive forces. That would be, again, think of like something pushed rightward. But if something starts to push leftward, you're going to get a force the other direction, and so that's going to perhaps take away from the motion, reduce the momentum. It depends on which way things are moving, but at any rate, it's going to have the opposite effect of what a positive force would have. So we have to treat this down below as negative area. Now that's something your geometry teachers would never want you to say is negative area, but in physics and in mathematics, we can certainly have negative areas. These are areas below the horizontal axis and above the graph. So then from here, it's really actually some geometry that you're probably familiar with. We just need the area of this triangle. So we have a base of 4, a height of 4, and the area of a triangle is 1/2 times the base times the height. So I usually have my students just indicate an area of 8. That's for this upper part. But don't forget to put your units down. When you're finding an area, you're multiplying a base times a height. So not only do you do that with the numbers, you do that with the units as well. The base units are seconds, the height units are in newtons. So we call this a newton second. And I want those in there because it reminds you of what that quantity means. It's an impulse, just like any force multiplied by a time. Well, what do we have down here below the time axis? We have a 1/2 triangle, and that's an area of 1, but we have to treat it as a -1 for that last 1 second that the force lasts. So what is our total? Total impulse, and you'll find in some textbooks they like to use the capital letter J for impulse. I've never been a fan of that. It just doesn't look right to me. But that would be a +7 newton seconds when we combine all of those together. Now sometimes I like to ask this. What if instead of this varying impulse or force that we have, or varying force that we had, what if we had a steady force? How much steady force would we need to have the same amount of impulse that this varying force gave us? Well, if we need 7 newton seconds and we have 5 seconds over which to do that, that's going to mean we need 7/5 of a newton the entire time. So that would be 7/5, about 1.4. So I'm going to find 1.4 here roughly on the graph. And I'm just going to draw this in just by way of comparison. This would be another force lasting that long that would accomplish the exact same change in momentum. Because if we shaded all this region here, I'm trying to do it in blue so it sticks out. I'm not sure it shows up very well in the video. But the area of that rectangular region is also +7 newton seconds. So that's just a nice way to find the average force. And in a calculus class, you're going to use this as a way of finding an average, and you'll know that by a different definition. So that's a pretty straightforward area. Now, I'm going to refer you to another video. If you ever come into a situation like this, suppose instead of just nice triangles or rectangles or trapezoids or something familiar, you may find a force time graph sometime that has something like a parabola. That's when you need to know a little calculus. So I'm going to make another video segment on how to use an integral to calculate an impulse. So refer to that if you need it. Hopefully this gets you through what you needed right now. Good luck.